competing on atoms. This is the ultimate computer. You can't do better than that.
Should we fear this change relative to any other?
They are millions of times more powerful than our most powerful digital computer.
Imagine you have a puzzle to solve. A puzzle so complex that it would take a regular computer thousands of years to crack it. Frustrating, isn't it? But now, picture a computer that can solve that same puzzle in a matter of minutes or even seconds. That's where quantum computers come into play. But recently, famous physicist Michio Kaku made a big announcement stating that quantum computers will transform our world completely by using artificial intelligence and replacing many AI tools, but this can pose a significant risk to humanity.
What quantum computing is going to be capable of, that's the kind of stuff we're thinking about, right?
Yeah, you see, quantum computers are the ultimate computers because they're competing on atoms. If there are aliens in outer space, and I think there are, it means that they also have perfected quantum computers, and they can do calculations that are far beyond anything that we can calculate with.
Quantum computers are a fascinating and revolutionary form of computing that harnesses the principles of quantum mechanics to perform complex calculations. While traditional computers process data using bits, which can represent either a 0 or a 1, quantum computers employ quantum bits or qubits, which can exist in multiple states simultaneously. This unique property allows quantum computers to tackle problems that are beyond the reach of classical computers. The history of quantum computers can be traced back to the early 1980s, when physicist Richard Feynman first proposed the idea of quantum computation. Feynman envisioned that by utilizing the principles of quantum mechanics, it would be possible to create a new kind of computer capable of solving problems that were impractical for classical machines. However, it was not until the 1990s that significant progress was made in the field. In 1994, Peter Shor, a mathematician at Bell Labs, devised a groundbreaking algorithm for quantum computers that could efficiently factor large numbers. This discovery was a pivotal moment because factoring large numbers is a task that lies at the heart of many encryption methods used today. Shor's algorithm demonstrated the immense potential of quantum computers in breaking conventional cryptographic systems, sparking both excitement and concerns within the scientific community. Throughout the 1990s and early 2000s, researchers began to explore various approaches to building quantum computers. One of the most promising technologies is based on the principle of manipulating individual atoms or ions to serve as qubits. In 2001, a team of researchers at IBM successfully demonstrated the concept of quantum computing by using nuclear magnetic resonance to control qubits. This achievement marked an important milestone in the field and showcased the practicality of quantum computation. As the field advanced, significant progress was made in developing more robust qubit systems. Scientists began to experiment with other types of qubits, such as superconducting circuits and trapped ions, each with its own advantages and challenges. These advancements paved the way for the construction of more complex quantum computers with an increasing number of qubits. In 2019, Google made headlines when it announced it had achieved quantum supremacy. Using a superconducting quantum processor known as Sycamore, Google's team successfully solved a complex mathematical problem that would have taken classical computers thousands of years to compute. This milestone demonstrated that quantum computers had the potential to outperform their classical counterparts in specific tasks, sparking a new wave of enthusiasm and investment in the field. Following Google's breakthrough, other major players in the tech industry, such as IBM and Microsoft, intensified their efforts in developing quantum computers. These companies, along with numerous startups and research institutions, embarked on a race to create more powerful and reliable quantum systems. In the quest for scalability, researchers faced numerous challenges. Quantum systems are extremely delicate and prone to errors caused by environmental disturbances, a phenomenon known as decoherence. To overcome this obstacle, scientists focused on developing error-correcting codes and fault-tolerant techniques to protect fragile quantum information from external interference. The year 2020 marked another significant milestone in the history of quantum computers. IBM unveiled its quantum computer, the IBM Q System 1, which was the first fully integrated quantum computer designed for commercial use. This marked a major step towards making quantum computers more accessible and practical for a wider range of applications. With the exponential growth of quantum computing research, the field began to attract substantial attention and investment from governments and industries worldwide. Recognizing the potentially transformative impact of quantum computers, governments began allocating significant funding to support quantum research initiatives. Quantum research centers and laboratories were established, fostering collaborations between academia, industry, and government agencies. As the field continues to advance, efforts are being made to overcome the remaining technical challenges and scale up the size and reliability of quantum systems. The goal is to reach a point where quantum computers can tackle problems that are currently intractable for classical machines, such as large-scale optimization, complex simulations, and machine learning tasks. Quantum computers operate on principles that are fundamentally different from those of ordinary computers, also known as classical computers. While classical computers use bits to store and process information, which can represent either a 0 or a 1, is quantum entanglement. It is a phenomenon that occurs when two or more qubits, the fundamental units of quantum information, become correlated in a way that the state of one qubit is intimately connected to the state of another, regardless of the physical distance between them. This entanglement lies at the heart of quantum computing and enables the development of powerful computational capabilities that are fundamentally different from classical computing. In classical computers, information is processed and stored as bits, which can represent either a 0 or a 1. These bits are independent of each other, and their values can be manipulated separately. However, in the quantum realm, qubits can exist in a superposition of states, representing both 0 and 1 simultaneously. This superposition allows quantum computers to perform parallel computations and explore multiple possibilities simultaneously. Quantum entanglement takes the concept of superposition even further by creating correlations between qubits. When two qubits become entangled, the state of one qubit becomes inseparably linked to the state of the other qubit, regardless of the physical distance between them. This means that the measurement of one qubit instantaneously affects the state of the other qubit, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance. The power of entanglement lies in its ability to establish intricate relationships between qubits. In a quantum computer, these relationships can be exploited to perform complex computations efficiently. Entangled qubits can be used to represent and manipulate vast amounts of information simultaneously, enabling quantum computers to solve certain problems much faster than classical computers. For example, consider a search problem where you have a large database and need to find a specific item. In classical computing, you would have to search through each item one by one until you find the desired one. However, in quantum computing, by leveraging entanglement, you can perform the search on all items simultaneously. This is known as quantum parallelism, and it can significantly speed up computations for certain types of problems. Furthermore, quantum entanglement also plays a crucial role in quantum teleportation and quantum communication. Through entanglement, information can be transferred between qubits instantaneously without physically moving particles from one place to another. This property has implications for secure communication and encryption, as any attempt to intercept the information would disrupt the delicate entanglement. Quantum computers excel in certain types of computations where classical computers struggle. For example, quantum computers have the potential to solve complex optimization problems, factor large numbers efficiently, simulate quantum systems, and perform advanced machine learning tasks. Quantum computers have shown great promise in the field of optimization, presenting a solution to real-world problems like route planning, supply chain management, and resource allocation. These problems often prove challenging for traditional computers due to their exponential complexity, resulting in impractical computation times to find optimal solutions. However, quantum computers excel in optimization tasks through the utilization of quantum algorithms, such as the Quantum Approximate Optimization Algorithm, QAOA, and the Quantum Annealing Algorithm, QAA. By leveraging quantum superposition and entanglement, these algorithms enable the exploration of multiple solutions simultaneously, leading to faster and more efficient optimization processes. The impact of quantum computing extends significantly to the realm of cryptography, where its implications cannot be overstated. Cryptography plays a vital role in ensuring secure communication and safeguarding sensitive information. Many existing cryptographic systems rely on the computational difficulty of factoring large numbers, a problem that quantum computers can efficiently solve using Shor's algorithm. As quantum computers advance in power, they pose a potential threat to these cryptographic systems. However, researchers have been actively developing quantum-resistant cryptographic algorithms, such as lattice-based and code-based cryptography, to defend against quantum attacks. The field of quantum-resistant cryptography aims to create algorithms capable of withstanding the computational power of quantum computers, ensuring the long-term security of our digital infrastructure. Another exciting application of quantum computers lies in the simulation of quantum systems. Quantum mechanics governs the behavior of particles at the microscopic level, and understanding and simulating quantum systems have been challenging tasks for classical computers. Quantum computers, on the other hand, are inherently suited for simulating quantum phenomena. By emulating the behavior of atoms, molecules, and materials, quantum computers can provide valuable insights into chemical reactions, material properties, and the behavior of complex quantum systems. This capability holds significant implications for drug discovery, where quantum simulations can accelerate the search for new drugs and optimize molecular interactions, potentially revolutionizing the pharmaceutical industry. The field of machine learning and artificial intelligence, AI, stands to benefit immensely from the power of quantum computers. Famous physicist Michio Kaku says that quantum computers' immense computational power could render current AI chatbots obsolete and introduce a new era of quantum-powered systems.
Quantum computers is the wild card. It could be a game changer. It could change the entire landscape of artificial intelligence.
The AI landscape has witnessed significant advancements, with sophisticated chatbots like OpenAI's ChatGPT capable of generating human-like text. However, these chatbots have inherent limitations. They rely on pattern recognition from training data rather than true understanding, leading to potential misinformation. Renowned figures like Michio Kaku and Geoffrey Hinton have raised concerns about the ethical implications of these AI systems. Quantum computing can address some of these limitations. Quantum computers use qubits that can represent multiple states simultaneously, enabling parallel processing and surpassing traditional computers' capabilities. Entangled qubits can instantaneously influence each other, enhancing computational efficiency. Quantum interference can guide quantum systems toward optimal solutions. These unique capabilities make quantum computers suitable for solving complex problems. The integration of quantum computing into AI could bring transformative implications. Quantum computers' exponential speed could expedite machine learning model training and improve natural language processing. They could act as powerful fact-checkers, verifying information accurately. Quantum computers could remove false information, serving as a check for AI software. However, integrating quantum computing with AI also poses risks to data security, as quantum computers have the potential to break current encryption methods.
In a 5 to 10 year time frame, quantum computing will break encryption as we know it today.
Protecting quantum computing innovations through patents is crucial to ensure their safeguarding. Patents promote innovation and provide inventors with exclusive rights to their intellectual property. While the United States and China currently lead in quantum computing patents, other countries strive to become leaders. Quantum key distribution systems are areas of significant interest. Challenges such as interoperability issues, high costs, and specialized skills hinder their widespread adoption. The advent of quantum computing may lead to the replacement of current AI chatbots with quantum-powered AI systems. These systems offer superior processing speed, efficiency, and accurate information verification. They can handle complex tasks, understand the context better, and provide reliable responses. In the realm of materials science, quantum computers offer the ability to discover and design new materials with extraordinary properties. Quantum simulations can explore the behavior of materials under various conditions, predict their electronic and mechanical properties, and guide experimental research. This could lead to the development of more efficient solar cells, stronger and lighter materials for aerospace applications, and novel catalysts for energy conversion and storage. Quantum computers could also revolutionize the field of quantum chemistry, enabling the accurate modeling of chemical reactions and the discovery of new catalysts for sustainable chemistry. The financial sector can also benefit from quantum computing. Tasks such as portfolio optimization, risk assessment, and fraud detection involve complex calculations and data analysis. Quantum computers can provide more accurate and efficient solutions, leading to better risk management strategies and improved fraud detection algorithms. Additionally, quantum algorithms, such as the quantum Monte Carlo algorithm, can be employed to simulate financial systems and explore the behavior of markets, allowing for more informed investment decisions.
The CIA is interested in this. All the big commercial banks are interested in this. Aerospace, energy, you name it, everyone is interested in who is going to be first.
Quantum computers hold great promise for solving complex scientific problems in fields such as astrophysics, cosmology, and particle physics. These machines can simulate the behavior of the universe from its earliest moments, helping us understand the fundamental laws of nature. They can aid in the search for new particles, analyze the large-scale structure of the cosmos, and simulate the behavior of black holes. Quantum computers can significantly accelerate scientific research, leading to breakthroughs that were previously unattainable. While the potential of quantum computers is vast, significant challenges remain on the path to their widespread adoption. Constructing practical and reliable quantum computers is a complex engineering task. Quantum systems are fragile and prone to errors caused by decoherence and noise. Building error-correcting codes and developing fault-tolerant quantum computing architectures are active areas of research. Additionally, scaling up quantum computers to handle larger problem sizes and improving the qubit coherence and gate fidelity are crucial steps toward practical quantum computing. Ethical considerations also come into play in the realm of quantum computing. The ability of quantum computers to break encryption methods raises concerns about privacy and surveillance. The computational power of quantum systems may have far-reaching implications for fields such as artificial intelligence and machine learning. It is essential to navigate these ethical dilemmas and ensure that the use of quantum computers aligns with societal values, preserving privacy rights and safeguarding against potential misuse. Technological challenges pose another area of concern for scientists involved in quantum computing research. Building practical quantum computers involves overcoming numerous technical hurdles. Quantum systems are highly sensitive to noise and environmental disturbances, making it difficult to maintain the delicate quantum states of qubits, the fundamental units of quantum information. Significant progress is required in areas such as error correction and qubit stability. The complexity of achieving scalable quantum systems raises doubts about the feasibility of large-scale practical quantum computers. Another consideration is the limited applicability of quantum computers. While they excel in certain computational tasks, they are not superior for all types of problems. Classical computers continue to be more efficient and practical for everyday computing needs. Scientists emphasize the importance of managing expectations and focusing on problem domains where quantum computers can offer tangible advantages. This selective approach ensures that resources are allocated wisely and that the development of quantum computing is pursued in a manner that complements classical computing rather than replacing it entirely. The development of efficient quantum algorithms poses its own set of challenges. Researchers are actively working on designing algorithms that can leverage quantum parallelism and quantum entanglement, two unique properties of quantum systems. However, finding suitable quantum algorithms for specific tasks remains a complex and ongoing research endeavor. It is crucial to carefully explore and understand the capabilities and limitations of quantum algorithms to fully harness the power of quantum computers. Furthermore, ethical considerations must be prioritized in quantum computing research and development. As technology advances, scientists are acutely aware of the potential ethical implications it may entail. Responsible practices and collaborations are essential to address concerns related to privacy, security, and the potential misuse of quantum technology. International discussions and the establishment of ethical frameworks are already underway to guide the development and deployment of quantum computers. By proactively addressing ethical considerations, the scientific community aims to ensure that the benefits of quantum computing are harnessed in a manner that respects human values and societal well-being. So this seems enough for today's video. Let us know your thoughts in the comment section. And for more videos, stay tuned.